All right, good morning, everybody. Welcome back. Hopefully you had a chance to at least sleep in a little bit. Glad to see everybody made it back here and is here in person. She's here. Anyway, I'm glad you guys all made it. Today is going to be a little bit, and I'd say this with a little bit of trepidation because I know it's early. It's going to be a little bit more math heavy than even maybe the typical day, but we're not going to go through all of it in detail. So I'm going to gloss over some of it with the understanding like all of the details don't matter so much, but what matter is some of the key results that fall out of it. Okay. So when we jump over details and you don't have all of the stuff in your notes, be okay with that because we're going to try to gloss over some stuff. But what will come out of it is some really kind of key ideas and ways to think about some of these problems. So that's the goal. More so than following every algebra part of the math that we're going to do. So the first thing that just to remind ourselves what we were talking about, we've been talking about how to find, for a simplified case like this, where we have a flat plate, this flat plate is at some constant temperature Ts. We have flowing over this plate some gas which is at T infinity and U infinity, some initial temperature and initial velocity, right? It's a gas flowing over this flat plate. One of the really important things to look at then is, of course, the boundary layer growth, right? So we're looking at and kind of trying to understand this boundary layer growth. We have two boundary layers growing simultaneously, one a velocity boundary layer, which is, we can think of as kind of a function of the no slip condition, the fact that at the wall things are stopped. So that kind of propagates up into the fluid. We start to feel it more and more and more as we go down the surface as time goes on. And the other one is the temperature boundary layer driven by heat transfer, kind of conduction really through that first layer of fluid. Things behave relatively well initially, but then we can get to this point where all of a sudden things kind of switch, and we switch from laminar flow, well-behaved, easy to do, or at least relatively so, to turbulent flow where we have things, the boundary layer grows faster, and all of a sudden we have, right, if this is delta, all of a sudden we have mixing and swirling and all sorts of stuff. So we have these two distinct regions. In the laminar boundary layer, we can calculate things relatively easily. In the turbulent boundary layer, we're going to see a little bit how we can get at that, but it's going to be a mix of experiments and kind of empirical models, semi-empirical models. So we'll see a little bit how we can get at that, but it's going to be kind of a mix. And then there's going to be some region here in the middle, which is the transition between the two, where sometimes we start to get some of these mixing things, but we're not kind of totally there yet. It can also be, there's some really flow and geometry dependent aspects to when this actually starts. But generally we can characterize when we're going to be in each different flow using the Reynolds number, just like we would in fluids. For those in fluids, we've just kind of introduced this. But we can look at which flow we're in. Using the Reynolds number. So Reynolds number is density times velocity times the characteristic length divided by viscosity. And mu is the viscosity. So we can look at basically where this transition happens by looking at the Reynolds number and what the value is at some given time. We'll see in a second how much of an effect or little of an effect that might have. But just as kind of a note, like high versus low Reynolds number depends on geometry, kind of first and foremost. So if you have a flow down a flat plate, that's one thing. If you have flow over top of a cylinder, that's another thing. If you have flow inside of a pipe, that's something totally different. So you have to know, like, what is the system that we're specifically talking about? But then other aspects of flow too, like fluctuations in our free stream velocity, if that's moving around a lot or if it's very steady, that's going to change where this transition is. Also, surface roughness. So it can be a little hard to figure out exactly without looking at the system exactly where the transition is going to occur, but you can at least get a pretty good idea if you look at other similar types of systems. Okay, and we'll see a little bit how that works in kind of experimentation in the real world in a little bit, how you would do that. For flow over a flat plate, you kind of have to look up, like, what's the Reynolds number equation for this specific system. But for flow over a flat plate, it would be density U infinity X divided by mu. Where X is the distance along the plate. So the Reynolds number is going to be going up as we go along the plate. Okay. For all problems like this, we're going to basically say, which regime are we in? Look at the critical Reynolds number. We'll call it REC. To see if laminar or turbulent. So we're going to have this kind of critical number, and if Reynolds number is less than the critical Reynolds number, then we're laminar. If Reynolds number is greater than the critical Reynolds number, then we're going to be turbulent. Okay, to figure out what the critical Reynolds number is, you have to do an experiment. So that's not something you can know just by knowing. That has to be something that you get experimentally for, again, a similar system, similar geometry, similar roughness. You have to be able to actually do that experiment to figure it out. Or you can look at somebody else's similar experiment and say, well, it's probably going to be about this. And that may be good enough depending on the exact system that you're working on and how accurately you need to know things. But we'll see here in a second how much of a difference that can make, exactly where that critical Reynolds, where this transition is in terms of convection. So I'll just write that. We need to find the critical Reynolds number experimentally for any given system. Okay, so let's look at a quick example and see kind of what that looks like. Okay, so we have a flat plate. Again, we're looking at this simplified case to try to start developing some intuition around what are the things that matter and how do they matter. So flow over a flat plate, we'll put some axes on this. That's Y and X. We have our flow here. So U infinity is 1 meter per second. Our plate is at TS. Let me see. Okay, so let's say this is at TS equals, well, we'll just call it TS because I don't think we don't actually need to care. But we'll say T infinity is, well, we'll do this. TS equals, sorry. No, that doesn't work. So we'll do this as 250. Sorry, everybody, it's 250K. And this is 350K. Okay, so the water, this is water flowing over a flat plate. So our fluid is water. We have a cold plate, and we're, I guess, warming it up with water. So we're going to ask, okay, what does convection look like? Because I can figure out the heat transfer as long as I can find the average convection coefficient. So all of the stuff that we're going to be doing is centered around, let's find H, and then once we find H, to use it like normal is super easy. So we're going to have some region here at the front end of the plate. Our boundary layer is going to be growing like this. And then we're going to hit some point, maybe, we're not sure yet, but we're maybe going to hit some point where all of a sudden we flip from laminar to turbulent. Okay, so here we have all of our mixing. And in this region, in the first region, we're fairly easy. So this would be, move this. because that's not pointing to that line. So this is the transition. Before that, laminar, after turbulent. So we want to figure out that dimension. We'll call that the kind of the critical dimension, XC, which corresponds to this critical Reynolds number where the transition occurs. And then for this particular case, we know the total length of the plate, L equals 0.6 meters. So our first step is to figure out, do we stay laminar the whole time, or do we actually have a transition somewhere along this 0.6 meters? And where would that be? So we have to look at the specific geometry of the system and say, where does the transition occur? For a flat plate, the critical Reynolds number is approximately 10 to the 5. So our first step is to find XC. So this part is always a little bit weird. So we have to kind of figure out, right, we have to figure out what temperature we want to look at, because viscosity and density are both functions of temperature. So we have this fluid, like far away it's at 350, but close to the surface it's going to be at 250 or closer to 250. So usually what we do is just use a straight average. Again, so all of these equations and all of the things that we're going to be doing to estimate convection are going to be much less exact than what we did to get conduction stuff, because they're kind of necessarily so, because conduction is super easy and we can get it pretty much exactly. Convection, we have to kind of wave our hands and hope we can get within 10%. So that's kind of our goal, is like if we can get ballpark right, that's about as well as we can do. And that's true for like kind of our handmade models, but also for like more advanced computer simulations. We're still looking for kind of a ballpark thing, not an exact thing. If you wanted to get a more exact thing, obviously you'd use a computer model, not some of these hand calculations. But the hand calculations, we're doing them because they give us insight into like, what are the important features? What should I be thinking about as I'm like kind of thinking about this system as a whole? So yeah, we're functionally, if you're doing a system and doing a kind of a more advanced simulation, you're going to be doing a more advanced thing than some basic hand calculations. But these, I think, can give us an idea of what are the important factors. So step one, find XC. So we know that that's going to be where the Reynolds number equals the critical Reynolds number. So this is density U infinity XC over mu. So like I said, we're going to use the properties at T average. That's not going to give us, again, this is for kind of these relatively simple hand calculations, but it will give us a good idea of how this works. So from table A.6, this gives us density is 997 kilograms per meter cubed, and viscosity is 855 times 10 to the negative 6 Newton second per meter squared. So we can plug in the critical Reynolds number is 10 to the 5, which equals 997. What did we say? It was 1 meter per second. Yeah, 1 meter per second. Times XC divided by 855 times 10 to the negative 6 Newton second meter squared. So this gives us a critical length of, 0.43 meters. So this tells us that about 2/3 of the way down the plate, we're going to get the transition from laminar to turbulent. So that, we think about what's happening here. We'll get 2/3 of the way down the plate, 0.43 meters as laminar flow, and then we'll flip, and the last third of the plate, the last 0.18 meters will be turbulent. So when we're trying to figure out convection, we have to treat those two sections as distinctly different because the dynamics in those sections are totally different, right? So we always are going to be treating like what's happening in the laminar region, what's happening in the turbulent region as two separate things. So in the laminar region, let's just kind of make up a model that we found from somewhere else. We'll see in a second where this comes from. So in the laminar region, H as a function of position is equal to a constant, we'll call it C lam, times x to the minus 0.5. Okay, this was just a model that I made up out of thin air. I'm not saying it's correct, but this is just a thing. So we're going to get we'll find ways to actually figure out what this would be. But we'll find some model. This is going to model the laminar region. In the turbulent region, our models are going to look very similar. So we're still going to have, H is still going to be a function of position. It's still going to be changing and decreasing as we go along the plate. Right, H is decreasing because the slope of the temperature at the plate is decreasing as we start to push more heat up into the fluid. Or as those temperatures get more and more similar. It's going to be C turb times x to the minus 0.2. So really similar, a different exponent on x, but we're actually we'll build our models of turbulent flow kind of based on our understanding of laminar flow. So these things are going to be fairly closely related. Those constants, C lam is 395 watts per meter to the 1.5 Kelvin, and C turbulent is 2330 watts per meter to the 1.8 Kelvin to make the units work out. So these constants can have kind of goofy units, but they work out to have units of convection. And then what we're going to do is use like these models will tell us, the models that we'll build will tell us the convection at a given position. What we have to do is use integration to sum it up over the whole section. So we want to use integration to sum up the laminar part over the entire laminar region, and then use integration to sum up the turbulent part over the whole turbulent region, and then look at the average over the whole business, the whole thing. So this will feel maybe a little bit weird. It's similar to what we did last time. So we looked at the average convection coefficient, which is really the convection coefficient that we've been working with all the time. We're just being a little bit more explicit now that this is an average over some region, so we're calling it H bar to make it a little bit more clear that it's an average. Right, and we said last time the average is 1 over L times H dx for this system. So we're basically putting our model of H in there, summing that over the whole position, over the whole length, and then dividing again by the length to get the average convection coefficient. So here we plug in or I guess we'd split into would be a better way to say it. We've split into laminar and turbulent parts. So we have to kind of split this to take care of both of these. And this is the part that I think conceptually it makes sense, but in practice, it's easy to make errors. So for this problem, we have a plate that's 1.6 meters. So 1 over 0.6 meters. We want to be integrating from 0 to 0.43. That's the part where we're laminar. So we integrate over the laminar part of C lam x to the minus 0.5 dx plus we want to integrate over the turbulent part, which is not starting at 0 because the turbulent part is like just the end part. So the turbulent part starts at 0.43 and ends at 0.6. So that, like, in effect, we're going all the way from 0 all the way to 0.6. But we do it in kind of 2 steps. We first go 0 to 0.3, then 0.3, 0.6. Then this is C turb x to the minus 0.2 dx. So this is going to be boxing that, not because it's super special, but maybe this will, when you have to think about these problems, this will be a good equation to come back to remember how to do that. Okay, if we plug in the values that we had, this gives us H bar equals 1 over 0.6 meters times, says 395 over 0.5 to be 0.43 meters to the 0.5 once we integrated and evaluated at those positions from 0 to 0.3 to be plus 2330. That's C turb divided by 0.8, 0.6 to the 0.8 minus 0.43. to the 0.8 if we actually went through and did that integration. These ones are always a little bit tricky because like you don't typically integrate x to the negative 0.2. But like the 0.8 comes down in front and then you get, because, right, so you'll have to play a little bit to make sure you remember how to do that. But, okay. Then we're simply plugging in these. We can find H bar would be 1620 watts per meter squared Kelvin. Okay. Okay, I think it's relatively straightforward once you get the hang of it. But I think about what we're trying to do. We're trying to first sum up over this one region, then we're summing up over the next region. To get a little bit of a sense of how important the turbulent region is and how like little changes in things can make things change a lot. Let's look at if we did this at 350K. We're going to get, so we raised the temperature of things so that, like, say the average temperature is 350. We're going to get slight changes in the, like, what C is, C lam and C turb. So now, C lam is 477 watts per meter to the 1.8 K. Is 3,600 watts. Or, sorry, this should be to the 1.5. This is to the 1.8. Okay. So we're going to get slight changes, but not a lot. If we look at our properties, density is basically the same, 974. Where it was 997, so it's changed a little tiny bit, like 2%. The big change comes in viscosity. So this goes to 365 times 10 to the negative 6 per meter squared. Okay, so what happens? We will get slight changes to these coefficients, C lam and C turb. We went from 395 up to 477. And for the turbulent one, we went from 2,300 up to 3,600. So like 50%. The bigger difference, though, will come because of this. So density changes by 2%. Viscosity goes down. So where we get the transition between laminar and turbulent goes down. So we get, let's find where that is. So XC equals the Reynolds number, the critical Reynolds number times mu over density U infinity. Critical Reynolds number stays the same. So basically our drop in viscosity directly drops this number. So we drop viscosity by a factor of 2. We're going to drop the critical Reynolds, drop this position by about a factor of 2. So this is 0.16 meters now, whereas before it was 0.43. So now instead of the first 2/3 of our plate being laminar and the last 1/3 being turbulent, we have like the first 1/3 being laminar and the last 2/3 being turbulent. This would, if we went and did the same procedure to find H bar, this would be about 3710 watts per meter squared Kelvin. So we would get effectively more than a doubling of the convection coefficient. And most of that is driven by the fact that we've pushed the laminar turbulent transition so that more of the plate is experiencing turbulent flow. So turbulence is going to be a huge part of what gives us the convection coefficient that we have. And if you're trying to design a system that you're trying to get good convection, you want to be thinking, what can I do to be able to trip turbulence so that more of my object is under turbulent flow and less of it is under laminar flow? Because laminar flow is going to be giving us worse convection than turbulent flow. So we can get like huge, basically, we didn't change anything about the geometry. We didn't change anything about the fluids. We just did it where we're at a little bit lower viscosity, like not even dramatically so. But that allowed us to get more of the object under turbulent flow, which gave us a factor of 2, more than a factor of 2 increase in convection coefficient. So that's something that just kind of a general rule of thumb. We want to be tripping the system so that more of it is under turbulent flow if we want higher convection coefficients. Yeah, Liz.
So when you're saying like let's look at it at 350 Kelvin instead of like the T average, what does that mean? I guess I don't understand.
So that would have to be, we would have to like change the temperatures in our system so that now the average temperature is 350.
Oh.
But if we did this at, just to see like how, depending on which temperatures you're doing the calculations at, you can get really different results. But there are other ways that we can trip turbulence. Like you could do something to the fluid to lower the viscosity. That maybe doesn't change other fluid properties that much, but it lowers the viscosity and makes it thinner. You could use like, I mean, if you're using like an oil or something like that rather than water, you could use, one oil that's high viscosity or another oil that's maybe similar properties but lower viscosity is going to give you more turbulence, which will give you better convection. Okay, so these are just kind of some broad outlines of some of the things that matter. When we're looking at flow in this kind of a region, so at this point, we haven't really shown where, a model like that might come from. It's going to be a semi-empirical model, so they're not going to be exact. Same with this guy, it's not going to be exact, it's going to be some semi-empirical model. What we're going to do next is going to show us kind of the general ways that we can think about attacking these kind of problems, both from a mathematical standpoint and maybe more importantly from an experimental standpoint. Like if you have a system, you want to understand what convection is doing, what kind of experiment do you need to design to be able to model your system under all of the conditions that it might perhaps experience. So we want to look, to do that, we want to look at, say something, again, we'll look at kind of the simplest case, but we want to look at what is happening in that boundary layer region. And by that, I mean, like, what are the physical laws that are governing what's happening in the boundary layer region? Like we have fluid flow and we have heat transfer. So what are there are 3 of them. what are the physical laws that are governing convective heat transfer? Okay. There are three of them. Does anybody have an idea of one or more than one, I guess, but start with one? Like, what are the three most important laws of physics that must work in that region that relate to what's happening there? Of what? Conservation of energy, I agree. So one, so conservation of energy must work still. It must be satisfied. Energy is still conserved in that region. And that's going to be obviously important with what's happening with temperature and heat energy and the flow of heat. Like, no matter what happens, we still can't be creating or destroying heat. Energy is still conserved. What other physical laws are governing what's happening in that region? Give you a hint. Conservation of momentum. So F equals ma. Yep. So Newton's second law, conservation of momentum, that also has to happen. That doesn't so directly relate to what's happening in heat transfer land, but that is governing the fluid flow part of things. So that also has to be satisfied. So both of these things must be happening, and like, we can't violate them. They're important to what's happening. What's the third one? I think I heard it. Conservation of mass. And fundamentally, we have to say all three of these things must work all at the same time, all in the same region, all in that boundary layer. So these are really the laws that are governing what's happening. So we can use these to gain insight. If we wanted to like get an exact solution for convection and how all this stuff's working, we would have to solve all three of these things exactly, all at the same time. So for those of you in fluids that had fun or are having fun thinking about the Navier-Stokes equation, this is like do the exact same thing, but now also do conservation of energy on top of that all at the same time together. So it's even more fun than just like figuring out what's happening with the fluids, because we also have to figure out what's happening with temperature. And right, in general, fluid properties are a function of temperature. So you got like that extra layer of complexity on top of that. So this maybe gives you an insight as to why these things are hard to do exactly and why we typically aim for pretty close. Because it's like functionally, it's just a lot of stuff happening. And even with computer simulations, we can't accurately represent all of it perfectly. So let's look a little bit before we dive into this. We have different types of fluid properties for gases and obviously liquids. Just some general notes. For gases, most properties are a function of temperature. So like density, obviously a function of temperature. Things will expand and contract. Most properties are a weak function of pressure. So pressure doesn't matter as much. Kind of the exceptions to that, density and viscosity are quite strong functions of pressure. So density and viscosity, pressure matters for gases. We often can assume ideal gas. And we typically assume incompressible. So just to explain what this word means, incompressible means that we have no density changes, or no density, not changes, variations is a better word. No density variations in the gas because of the motion of the fluid. This works if the Mach number is less than about 0.3, right? The Mach number being the speed of sound. So this is about 100 meters per second in air. Okay, we're not in this class going to be doing things with like really fast velocities. 100 meters per second, that's like 250-ish miles per hour. Once you get above that, we get close enough to the speed of sound that you actually start to get density variations because of the motion of the fluid. Right, eventually, when you get to the speed of sound, you get a sonic boom, which is like pretty big density variations in the air. We're not going to talk about what's happening in there because it's even more complicated than what we will talk about. But generally, those are kind of some things that we'll use. For liquids, so most properties only weak function of temperature. Kind of the exception to that is viscosity. The other potential exception to that, the thermal conductivity, is about constant for water. But not all fluids. So there are fluids where the thermal conductivity does change with temperature. But really for fluids, all properties are a weak function of pressure. So pressure never really matters for fluids. Temperature does for some specific properties, but not that much. Mainly viscosity. The main effect that you have when you change the temperature of a fluid is it gets like quote unquote thinner. Most of the other properties like heat capacity and density and thermal conductivity, most of those other things stay basically the same. So you can consider like the problem we did last time. The big effect is that we get lower viscosity, which gives us different behavior. These are almost always incompressible. Okay, we almost never need to care about density changes in liquids unless it's kind of a really specialized case. So we'll look again at our simple flow over a flat plate, again, to kind of say, okay, what are these, if we wanted to take, we're going to use a lot of these simplifications. They're not all true. So I wanted to lay out like which ones are true and kind of when are they true. They're not all true all the time, but we're going to use them to simplify things again, because we're not, especially what we're going to do now, we're not really building toward an exact model. We're building toward what are the key features that we can use then to kind of key in on and say, these are the things that matter. And if we're doing an experiment, these are the things that we need to try to find. So we'll see a little bit how that works. We're going to look now at a general case and say, what about these three physical laws? Conservation of energy, Newton's second law, conservation of mass. Okay, so the simple case that we're going to look at, same thing. So we're going to have we'll have steady laminar incompressible flow. So we're going to have the simplest possible flow. We're going to have 2D parallel flow over a flat plate, right, which is the simplest geometry. And no gravity, and constant properties. So like mu, rho, k, Cp, alpha, etc. Anything that's a fluid property, all of these things are really functions of pressure and temperature in different ways that we just talked about. We're going to forget about all of that. So this is like, let's take real life and simplify it down to the most basic possible case. Turns out that's even pretty hard to do, to actually solve. But it'll give us some insight into more complicated things that I think is really instructive. So what this looks like, again, we've drawn this a whole bunch. Here's our flat plate. You're getting sick of drawing this, I bet. Here's our flow here. So this is U infinity, T infinity. Our plate is at a constant temperature Ts. So if we looked at what's happening to the thermal boundary layer, it's going to be growing as we go along the plate. If we look at it at, say, 1 point, I don't know, down here, it's going to be something like that. So this is delta T of X. That's the thermal boundary layer. That's not an infinity. T infinity. If we looked at some point at the velocity boundary layer, that may be changes like this. So this is delta of X. That's going to look like this. This is U infinity. So in general, we have these two boundary layers growing. They're in general not the same size. The temperature boundary layer can be thicker or thinner than the thermal boundary layer. We've already talked a little bit about this, but we can relate the thickness of these two by the Prandtl number. Right? We did some of the math of this on that one in-class thing after we watched the video. So the relative thickness of these is related to what we call the Prandtl number, which we usually call PR, right? Which is the relation of the kinematic viscosity and the thermal diffusivity. That's mu over rho, and thermal diffusivity is K over rho Cp. Right, so Prandtl is this ratio of momentum diffusivity over thermal diffusivity. It gives us the relative, like which is faster. Do momentum changes propagate through something, or do thermal changes, do heat propagate through something, which is faster? It's a relation between just physical properties of the fluid, like mu and rho and K and Cp. So we can actually know this, like you can just look it up. What's the Prandtl number for some fluid? And this will tell you the relation between the different boundary layers. So for Prandtl, if Prandtl is less than 1, then delta is less than delta T. So again, this would be something like that. So here's the thermal boundary layer is really thick, but the momentum boundary layer is really thin. That's the situation that we just drew. This happens kind of most dramatically with liquid metals. It can happen a little bit with other things. but most dramatically with things that have really high thermal conductivity. So heat goes through them really fast, but momentum changes don't. So something like a liquid metal. If the Prandtl number is about equal to 1, then that means that these are about the same, so they might not be exactly the same. If it's not exactly 1, but they'll be, kind of, that's a bad one. So they'll be in the same ballpark. They'll be similar thicknesses. This happens with gases. So for gases, all gases have Prandtl numbers of about equal to 1 because the mechanism for thermal transport in a gas is like fundamentally the same mechanism. It's molecular collisions. So the mechanism for thermal transport and heat transport are the same. So you end up getting boundary layers that are basically the same. Prandtl number, sorry, P, greater than 1. That means that delta is greater than delta T. So that means we have, like here is delta, so their momentum changes up pretty high in the fluid, but all of the heat transfer action happens kind of within that delta T. Which is true of water and oil. So for water and oil, really all of the heat transfer action happens in a smaller distance than like the momentum stuff. Okay, so if we're looking at we're trying to look at the physics that's happening. So we have to look at kind of all of these things. We're going to be making lots of simplifications. Again, we're going to be going through this relatively quickly. You'll go through parts of it in a little bit more detail. But we'll look at 2 simplifications kind of right off the bat. The first one is that changes in temperature or velocity are much faster in Y than in X. So like the vertical dimension, things are going to go from like hot to cold really fast, but there's only going to be relatively gradual change from left to right. So this would tell us that d squared u dx squared is relatively small compared to d squared u dy squared, where u is the velocity. And d squared t dx squared is a lot less than d squared t dy squared. The other thing that we're going to say is that the change in pressure is about equal to the change in pressure at infinity, which equals a known quantity. So there are going to be pressure changes in the boundary layer, but we'll kind of forget about that. Again, you'll see maybe how some of this comes about. So we would calculate this with fluids type stuff. Okay, so what we want to do is look at heat transfer. So the heat transfer at the surface we looked and showed that this was true earlier. So there's conduction in the surface through that kind of first layer of fluid. That equals H Ts minus T infinity. Right, this is saying that conduction or convection is really conduction through that first little bit of fluid. Because that first little bit of fluid is stationary because of the no slip condition. We're going to take this and you've had some practice doing this, but we'll non-dimensionalize this. And we're going to do this for kind of the same reason that we did it when we were looking at 1D conduction. We're going to do it so that we kind of get all of the units out that we can. And that will give us, like in 1D conduction, we got all of the units out of the exact, like this time-dependent 1D conduction. We got all of the units out except the BO number kind of hung around. So we said, really the only thing that matters is the BO number. And then we can use that to figure out all of the other stuff. We're going to do basically the same thing here. We're going to try to get all of the units out so that we can say, what are the key features of this problem? So we'll non-dimensionalize this similar to how we non-dimensionalized our other stuff. So we get y star, which are going to be our non-dimensional variables, is y over L. T star is T minus Ts over T infinity minus Ts. So this is really similar to what we called theta star before. I don't know why our book changes notation, but I'll change notation with the book so that when you go and look at that, when you look at some of those models, that makes sense. We would do the same thing. This would get us, right? So y equals y star L and T equals T infinity plus T star TS, not T infinity. TS plus T star minus T infinity minus TS. Okay, we would just do some basic algebra, and then we would take these and plug this in anywhere we saw T, and take that and plug that in anywhere we saw Y. Right, that's our general strategy for non-dimensionalizing things. That would give us d T star dy star evaluated at y star equals 0 equals H L over K F. This should look really similar. HL over K is what? Remember the non-dimensional group that is? HL over K is the BO number. This is super similar, but it's not a BO number. So this is, we call the Nusselt number. NU. Right, so new salt is not equal to BO, although they're very, very similar. So I'm just going to circle that, put an exclamation point by it. They're not the same. The BO number is talking about what's happening in the solid. Right? The BO number is talking about temperature gradients in the solid. The new salt number is talking about temperature gradients in the liquid or the gas or whatever it is. So new salt so they come about in like similar types of situations. Convection at a surface. BO is talking about what's happening inside of that solid. The new salt number is talking about what's happening inside of that fluid that's outside. So they're really similar. They have HL over K. The BO number is HL over K. But the kind of fundamental difference is which side of the thing are they talking about? Are they talking about inside the solid, or are they talking about inside the fluid? But the new salt number is going to be super important because that's talking about directly. If you know the new salt number here, that's talking directly about the temperature gradient in the fluid. So we'll write that explicitly. So new salt describes the temp gradient in the fluid at some point on the surface. So if we can find, because convection is conduction at the surface in the fluid, if we can find the new salt number, right, the new salt number is going to be giving us what's happening at the surface as far as convection happens. So this is like kind of our key point, and we're going to develop strategies to be able to figure out what is the new salt number, and then use that to figure out what's happening as far as convection. So the new salt number really describes fluid convection at surfaces. So we'll see, I'll just kind of write some of the basics of this out now. If we looked at, again, I'll go back and draw the same picture. I know we're kind of getting sick of drawing this picture. So T infinity, U infinity. Let's imagine this is delta T of X. That's delta of X. We would have some velocity boundary layer here. We would have a temperature boundary layer here, T infinity, U infinity. What we're going to do to solve these differential equations, we're going to define a little area, and we're going to skip over all the derivations of this, but right, how we would do it, we did this in more detail in fluids. If you are taking that, or you took that a little while ago, we're going to define this little tiny piece of fluid we're going to look at the fluid flow through that piece of fluid and use that to build up our description of conservation of mass, F equals ma, conservation of energy. So this is our fluid. So we're not going to do this in any detail at all. We'll just look at the result. So conservation of mass. What would that look like? That would be du dx plus dv dy equals 0. Okay, u is the x velocity, v is the y velocity. Newton's second law would be, this is a simplified version, so this isn't the exact one that you've seen in fluids, if you've seen it there, but it's close. It's a simplified version of it. du dy equals minus 1 over density dp infinity dx plus kinematic viscosity. So I'll try to make this, that's a swoopy v, mu over rho, d squared u dy squared. Okay, so I'm like building in some of the simplifications that we used earlier. We're kind of diving into even the simplified versions of what these are. So this is mu over rho, just to remind yourself. Then conservation of energy. What that would look like is u dt dx plus v dt dy equals alpha d squared t dy squared plus nu over Cp du dy, and then that whole quantity is squared. So that's not d squared u dy squared, that's du dy quantity squared. So what we're going to do next time, because we're out of time this time, we're going to take these differential equations and show these are the things that matter. These are, if we could solve these exactly, these would give us the answer, but we can actually get an insight into what are the key features, what matters, by looking just at the units and non-dimensionalizing these things. We'll see a little bit how powerful that can be. We'll jump into that next time. The one comment, I guess, about this week, there is a homework assignment due Thursday. It's posted now. It's pretty short, so it shouldn't be too crazy. Yeah, it is fairly short, like calculating a Reynolds number and one integral, so I don't think it'll be too bad. But that's due on Thursday. So come to class with that. It'll be a little bit lighter of a homework assignment, not anything crazy. But with that, have a good rest of the week, and I'll see you guys on Thursday. A good short week.